Hi guys, Buildzoid here, and today we are going to be doing a video about why blower heatsinks suck so badly. Um, and this is just like a thing that I wanted to talk about for, like, I think I've shot this video in the past, and then it never turned out good enough, so we'll see if I'm more successful this time. Um, Anyway, so we've got our two bricks here for our GPUs, and this one's going to be our blower example, and this one's going to be our axial card. Whoa, we're just going to do a two-fan design, right? And, okay, no, that's terrible, but whatever, who cares? It doesn't need to be super accurate. So, we've got our two GPUs here, and the basic problem with a blower heatsink, with blower heatsinks is that basically any cooling system is about having, as large a heat exchanger as you can possibly have. And then flowing as much coolant through your heat exchanger as you possibly can. Because the more coolant you run, because basically with your the bigger the heat exchanger, the more coolant you can potentially run through it, or the longer the coolant can, interface with the heat exchanger. And then why do we want higher coolant flow? Well, the bigger the temperature difference between our coolant and the heat exchanger, the faster heat is going to transfer between the coolant and the heat exchanger. So, if you have coolant, so that's basically it. And so let's get to why blowers are so bad compared to, open air cards. So, if we, in terms of the heat exchanger situation, they should be relatively comparable, right? On a card like this, you're going to have basically a fin stack that's going to take up, all the space under the fans, basically. So it's going to be, it's going to be a very long fin stack, but it's going to be a relatively low fin stack. It's not going to be very deep. Whereas our blower heatsink, well, it's going to have a fin stack that's very tall and ends about right before where the fan starts. So you're going to have a fin stack that looks more like this, right? You're going to have a fin stack that looks something like that instead of what you have in this card over here where the fin stack's really low but really long. So in terms of heat exchanger size and surface area, they can be very similar. Now, obviously, we do have a lot of, open air cards that are like 2.5 slots thick, 3 slots thick. I think Gigabyte for the 3090 is doing a card that's like 4 slots thick. So yeah, a lot of the time, but we're going to consider equivalent physical dimensions of the GPUs. So both GPUs are going to be 2 slots. Now, so we have our two fin stacks, right? And we've got our fat fin stack that looks sort of like this. And then we've got our fan over here, right? And that just pushes air into the fin stack like so. And this is where the problems begin. Oh, and then of course we cannot forget that at the end of our GPU we have a bunch of display outputs, and then we have like a DVI port over here. And so basically, the first problem with blower heatsinks is the flow part, right? Like our goal is to flow as much coolant through our heat exchanger as possible. So ignoring some other issues with our heat exchanger choice, the fact that we have all these display outputs in the back, and admittedly AMD has a lot of GPUs where they've stopped putting ports into the top half of the slot because they keep having cooling problems with their crappy blowers. You still end up with this situation where you have, the rear exhaust, and that rear exhaust isn't completely open. It's normally some kind of grill. Why is it a grill? I don't know. I really think it would be better if it was just a gaping hole, because with the grill on there, you end up with a, instead of having 100% opening, you have maybe 80% opening, 20% metal. And so that is more restrictive to airflow than 100% opening, right? In fact, one of the sort of simple things you can try with blower cards to try and improve their airflow is to just remove and improve their cooling as a result, is just remove the rear I/O bracket. Just get rid of it. Or, because if you want the tabs that come at the end of that, you can actually just, with a lot of AMD reference cards, those are affixed with 2 screws right here. So you can just cut off all of this. You can just get rid of that. And you can just keep the tab part. And that'll bolt down to the base plate of the GPU. So you'll still support the card by the PCIe slot, but you won't have you won't have the very airflow restrictive grating anymore. So that's one of the big problems. Is just okay, so we've just blocked off most of our exhaust area. straight up. It's just like, yeah, and the problem with this is, of course, like, okay, so on our open air card, right? Where does the air come out of an open air card? Well, it comes out here, it comes out there, it comes out over there. Depending on how the fin stack is oriented and how the heatsink is designed, some of it is going to blast out the rear, some of it's going to blast out the front. It's just going to spew air everywhere. And there are some downsides to this. Like normally the air coming out the bottom of the card tends to recirculate because there's a motherboard right under it. And so the air slams into the motherboard, washes off, and ends up back like getting pulled back into the fans again. And so you get used air recirculating like this. But if you have good internal like airflow, you can actually blow, like if you blow air, like fresh air into the system across this way, you can completely negate that basically. And then these open air cards get like, it can actually make a pretty significant difference to the cooling performance. So that is that is something to consider. Also, you can like like the thing is, I run open air test benches, so if I'm running an open air card where I notice that there's a lot of, well, actually I normally just put a fan in front of it to disperse all the air building up in front of it. Because that's the thing, like if you leave just the two fans alone, they will literally just recirculate the same air over and over and over again. Whereas if you build up a, positive pressure zone in front of the heatsink, and that positive pressure zone is fed with fresh air from a different fan standing far away from the card, it's actually going to send all of that spent air off to the sides. And yeah, so you can improve the efficiency of this kind of cooling system by tweaking the airflow in front of it. With a blower, you're pretty screwed. There's not really anything you can do. It's just like, what the fan doesn't pull it. I guess you could try put like a really high like a really high pressure fan directly in front of the intake to just cram more air into it, but that's just going to make it even louder. So, good luck with that. Which admittedly, even the fan in front of this is going to make it somewhat louder, but you don't need that much airflow. Right, you don't need to like you don't need like a 3,000 plus RPM fan to just disturb the hot air buildup in front of an open air card. You just need like a gentle breeze, and it'll make a huge difference. So anyway, so the first problem we run into is just like, well, this has maybe, I don't know, 8 times as much open like exhaust area, 10 times. I'm not going to do the math on that. It's not really practical. But the main point here is, because this has so much more exhaust, like open exhaust area, in order to get the same amount of airflow, you would need, say, like, let's say this has 10 times as much exhaust area. You need 1/10 the airspeed to get the same amount of airflow through the heatsink. What does that mean? Well, more airspeed equals more turbulence equals more noise. Let's not also forget that, like, to get a high airspeed out of a small blower, like out of our blower fan, you're probably going to need to crank the RPM. So then you're going to get like bearing noise and all of the turbulence from the fan going fast. So basically, this sucks because you're trying to cram a lot of air through a very small opening instead of trying to cram the same amount of air through a much bigger opening, right? Because that's the thing, is like air has a fixed amount of like cooling capacity that it offers. And so if you have a similar size heat exchanger, the only way you're getting more cooling out of it is to shove more air through it. There's really nothing else you can do, and that's where like open air cards have their first big advantage. They're just more open. Therefore they can flow more air, therefore they can do more cooling. Now, the other problem that you run into with blower heat sinks is the fin stack. They've literally, like, the way the way the air is shoved into the fin stack is literally the worst possible way. So we have our fat, stubby heat, like we have our fat, thick, long fin stack here compared to our, let's say, significant, actually, I'm not sure that it would be that much thinner, but, and here we have our thin open fin stack, right? And then we've got our 2 fans on top of that. And so, and like here again, you can clearly see, like, the thing is, if like cool thing about cards with short PCBs, especially like R9 Furies are great about this, is if the PCB ends like here, then you get so much airflow in this area. Like, it's absolutely ridiculous how much, like, the having the PCB end before the end of the fin stack is so good for airflow. It's a real shame that like more manufacturers don't mess around with that. Oh, I actually have a really interesting GTX 670 that has a kind of funky little airflow optimization in the PCB. We're gonna look at that. I don't think it's that effective, but it's kind of cute, and I think it's neat. So we will be seeing that eventually in a PCB breakdown if I ever get around to it. Anyway, so here we have our two fin stacks, right? So this fin stack, you just shove air into it, and it just goes through, and then it has to wash off the PCB of the card. This fin stack, it has to go all the way through the fin stack sideways. And this is really bad because at low air speeds, let's say we're pulling in 20-degree air. So as soon as the air meets the fin stack, it's going to start heating up. So at the start of the fin stack, we're going to be at, say, 20 degrees Celsius. And then by this point in the fin stack, we might be at 30. And let's say our fin stack is at 60 degrees, okay, which is pretty hot, but this is just examples. So, and we're at a low air speed. So we get 30 here, we get 40 there, 50 here, and 60 at the very end. So the air coming out of this fin stack is now at the same temperature as the fin stack itself. Do you know what this tells us? We need more airflow, because basically in this last stretch right here, the thermal transfer between the surface area over here is terrible. It's just really, really bad, because the temperature difference between our fin stack and the air in this area is like 5 degrees on average. We'll just pretend that it's that simple. It's not actually that simple, but I'm not going to get into that. But so whereas like in this first part of the fin stack, the temperature difference between our air and the fin stack is what, like 35 degrees on average? So much, much bigger. And therefore, thermal transfer over here is much better than thermal transfer over there. But it gets worse as you lower the airspeed, because if we lower the airspeed further, instead of hitting 60 degrees by the end of the fin stack, we might be hitting 60 degrees, let's say, I'm not sure how it would scale, but if you hit 60 degrees by the middle of the fin stack, the end of the fin stack doesn't do anything anymore. This is literally wasted surface area, because the air has now reached the same temperature as the fin stack. They are at equilibrium. No more thermal transfer can happen. You need more airspeed. So you just have to keep cranking up the airspeed in this, and this is just bad. So like shoving air through the fin stack the long way just means you're going to end up with a lot, like the fin stack is effectively less efficient, because the air coming out of it is like towards the end of the fin stack, the air is starting to get really close to the actual temperature of the fin stack itself, which is bad for thermal transfer. Now, with this heatsink, if we have very low air speeds, we can actually end up in the same situation where at the top of the fin stack, we have 20-degree air, and coming out the bottom, we have 60-degree air. But if we use the same airspeed as this blower heatsink, the air has to travel, the air is traveling this much distance instead of this much distance. So actually, basically, if you were shoving air into this fin stack at the exact same velocity that this blower is shoving it through this fin stack, which admittedly would probably translate into a very noisy open air card, but the cooling would be incredible. You'd end up with 30-degree air coming out of the fin stack. The entire time that the air is inside the fin stack, it would be massively cooler than the fin stack. And so the heat transfer between the fin stack and the air would be really, really good. So basically, that's another advantage that open air cards have that compared to blowers, is just because the fin stack is so shallow, you can actually use lower air speeds and still get really good efficiency, because you're shoving the air you're shoving the air into the fin stack through a shorter, through a less depth, right? So the air has less time to heat up, and it is at peak thermal transfer efficiency for more of the time that it is in the fin stack. Because basically, once the air is at the same temperature as the fin stack, it doesn't do anything. And this is really counterintuitive for a lot of people. A lot of people think that if you crank up the water flow through a cooling loop, it makes it worse at cooling, but no, because you end up in the same situation. If the water coming out of your water block is at the same temperature as the metal of the water block, you need more water flow, because your water is at some point inside the microfins, your water stopped doing any thermal transfer. And the same thing applies to air. If the air coming out of your heatsink is at the same temperature as the heatsink, you need more airflow. It's really that simple. So that's another advantage these kinds of heatsinks have, where it's just you can shove the at the same airspeed, the air is gonna be you're gonna be getting basically way more fresh air through the heatsink Because that's the other way to look at it. Like, once the air is at 60 degrees, it's used. It's spent. You can't get any more heat into it. Whereas here, you're not going to run into that issue. And so you can consequently lower the air speeds, and you're still not going to run into that issue. And then we're also not, and then also factor in the fact, like, also consider that the same airspeed with this, like, because we're basically comparing, like, this cross-section versus the side of a blower heatsink, right? Because if you look at a blower fan, like, it blows air out this way. So we have this cross-section versus this cross-section. So again, we also have that cross-section benefit in favor of this. And so, yeah, blower heat sinks. And the funny thing about this situation with the blower heat sink fin stack is this is literally the worst way you could try to cool this, like, cool an object shaped like this. Because basically, this, like, choosing to blow air through the card this way maximizes the depth of the heat exchanger and minimizes the cross-section. Right? We want a more cross-section so we can shove more air into the fin stack at a lower airspeed. This is the worst way of doing that because this is the skinniest part of the entire, like, that is the skinniest dimension of the heatsink. Like, you'd have more air, like, you would need less airspeed going this way than, using a blower. Now, the reason why you don't really see heatsinks that blow air through the card this way is because that's just, like, it's pointless. Like, it's more like, well, there's a bunch of things to it. So one, you'd need to use like 40 millimeter fans. 40 millimeter fans have one major flaw where they're basically more fan hub than fan blade. And so they actually kind of suck at moving any air. So that's one problem. The other problem is, like, you're not actually, like, the whole reason why we even have blowers is that the goal is to exhaust all of the heat from the GPU out the rear of the system, which if you had a heatsink which was blowing the air through the shroud sideways, well, it's still ending up back in the system. So why are you just, like, why would you do that when it's literally, like, you're using less efficient fans, you're still chucking all of the heat back inside the case? Just do this. This is way more, this is also simpler. You need less fan hubs, right? Like, that's the other thing. Consider how many like, if you're doing 40 millimeter fans, a card is like 200, and a lot of cards are like 270 millimeters. You're going to have like you're going to have like 6 40 millimeter fans on the side of the card. That is going to be significantly more expensive than 2 fans, right? So that's why we don't see heat sinks where they shove air through the fin stack sideways, because that's just dumb. It's less dumb than the blower. Well, actually, it's probably worse than the blower, mostly because your 40 millimeter fans are mostly fan hub. But from just, like, if we ignore the fact that 40 millimeter fans are terrible, it's not actually, like, it wouldn't be that bad an idea. But blowers are really, like, yeah, you literally couldn't choose a worse direction to try shove the air through the fin stack than this way. So, yeah, and that's why blower heat sinks suck so much. It's just like, you are trying to, because at the end of the day, you need to move, like, 1 cubic meter of air has a fixed amount of heat it can transfer for, like, there's 1 cubic meter of air has some thermal capacity, right? And our goal is to take heat from the fin stack and stick it into this air. And so, and the rate at which this happens depends on the difference in temperature between the air and the fin stack, right? So if the air is at the same temperature at the fin stack, well, we can't transfer any heat. And the other thing is, like, so basically our goal is to take as much fresh air, like, and just shove it into the fin stack and through the fin stack as quickly as possible, because it'll naturally pick up heat as it's going through. Like, we don't really need to do much in that department. Like, there is some science to, like, getting better thermal transfer between air and the fin stack. Like, I think there's something about, like, you want actual turbulence in the air, because if you just shove the air in sideways and the air is flowing really clean, then, and the airflow is really clean, then you end up with, like, a surface of air right up against the fins that isn't really moving and is actually very close to the temperature of the fins. whereas the air that's actually flowing through the heatsink isn't really getting in contact with the fins. So, like that's where you get all the like fancy non-straight fin geometries that you see on a lot of heatsinks, where they'll be like, oh, we have 3D fins for better thermal transfer. That's where that comes from. You can't have that in a blower though, because you barely have any airflow as is. So you can't, like, because obviously if the fins are really bumpy and non flat, then they're going to be more air, like, restrictive to airflow again, and it's just like, yeah, so you can't do that in a blower because you're already struggling to get any air through that heatsink thanks to the fact that the fin stack's so deep and that the opening at the end is so small. And admittedly, blower fans have a lot of static pressure, so it's not really that big a problem. But for all of the static pressure they have, they don't really move a lot of air. So, like, sure, the air's not going to stop in the fin stack anytime soon, but it's also not moving very quickly. So you're still screwed on the cooling situation. So, yeah, that's why blowers suck. Like, trying to cram air through a GPU this way is dumb. It was always dumb. Except, like, the thing is like, I get that the whole argument for using blowers is like, oh, but now we exhaust the 200 plus watts of GPU heat out of the case the most direct way possible. But in a lot of systems, I'd say the GPU probably takes priority over everything else. And I actually would argue that we could design better cases and then not have to compromise the cooling of literally the most power hungry component in the entire system by just not having crap case design. Like that, in my opinion, like, because basically this exists to address design flaws elsewhere. And this in itself is a design flaw. It's just like, okay, so we have a crap case, therefore we're going to have a crap cooler on the card. It's like, no, make a better case and then design a proper heatsink for the card. This is just fixing a problem that started somewhere else. And like the problem really comes from the fact that GPUs, like, it's like GPUs as PCIe cards, just from a power delivery perspective, don't make a lot of sense, right? Because the PCIe slots, when they became a thing, like, you didn't have GPUs that pulled more power than CPUs. So it makes sense that, like, the fact that someday we're going to have 200 and 300 watt GPUs going into PCIe slots that are going to be 2 slots thick was never factored into the whole cooling situation. This is where that comes from, is just like, yeah, nobody considered that we might have to deal with 300 watt, heat outputs in this form factor. But even then, I think, just like better cases, better GPU heat sinks is a better solution than bad cases with really bad heat sinks. Or, well, it's not even like the heatsink is fine. It's just the whole overall, the cooling system is just like, this is bad. This is really, really bad. So, yeah, there. Thank you. That's my thoughts on blower heatsinks. It's just like, I feel like this video is unnecessarily long. But I've already reshot it once, and this is the second this is the second reshoot, and that's ignoring all of the times I might have tried to make this video in the past, because this is a video idea that I think I've had for over a year. I really do need to check if I've already uploaded this video, though, because I'm not sure. Funny thing about me and making videos. But yeah. There, that's it for the video. Hopefully this made some sense. I'm not a, like, thermal engineer, but it's just like, from my understanding of thermal physics, blower heat sinks are just, like, on a fundamental level, you could not choose a worse way to air cool a GPU than with a blower. Like, actually, no, the 40 millimeter fans on the side is probably worse. but like, ignoring that, blowers are just bad. Okay? This is a really bad way to do your heatsink. Another consideration is that blowers only take in air from the top, and because normally there's just walled off with PCB down here, which, like, you could maybe squeeze more fresh air into a blower if you have it intake on both sides, which some cards do that. It doesn't really make much of a difference to the fact that you're still trying to, squeeze air through this opening at the end of the bloody card, so it still sucks, but It might suck slightly less. Actually, more like sucks more, because now it sucks from 2 sides instead of just one. But yeah, anyway, that is it for the video now. So yeah, thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. And what else is there? All right, there's also the HOC Teespring store, where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. And both of those help out immensely with running the channel, so if you check them out, that would be much appreciated. And yeah, that's it for the video. Thanks for watching, and goodbye.